Now let's move on to more advanced topic, and this will actually cover the background for your second assignment after the bomb lab. The first thing that we'll discuss is, we'll talk about the memory layout of a process. A process, which we will learn more in detail, is a program that's being executed on your basically computer. For each process, so a process is a running program. For each process, we have allocated a space, a virtual address space, and this is called virtual because we're not referring to the physical memory. Rather, each process thinks that it has access into a memory space that's clean. That means that it has a memory space that starts from 0000 to all this number, okay, which is actually 2 to power, basically you have 48. And for this, basically this allocation is forms the idea of a virtual memory. So we will cover this in detail towards during the last 2 weeks, plus in the operating system. But the idea is each process thinks that it has this clean memory, regardless of what physical memory, how much physical memory you have in the system. And this is true. This is an illusion, okay? And this is provided to all the processes. So every process that's running thinks that it has this clean slate of memory, and everything is located in that. And we will be seeing that how this space is allocated is mapped onto the physical memory system that's basically implemented by a virtual memory system, which we will, as I said, cover later. So in this case, the virtual memory has a particular layout, okay, that is shown in here. So if this is the address, like this is the address space, and we have basically a stack, which is starting from this address and it goes down. Then from 4000, we have text, which contains our executable machine instructions and which is read-only. And then we have the data, which basically has this statically allocated data, global variables, static variables, string constant, etc. And then we have the heap, which is dynamically allocated as needed. Such. And then we have basically some shared libraries that are used in here. And for the stack, we have an 8 megabyte of limit. We can understand and check this on your system by doing this, writing this simple memory allocation example, and then using GDB to analyze the addresses. So here we have this simple thing, and we declare these are global variables. So we declare two variables. One is big array, which is we take a 1 long and shift it by 24, leaving this is 2 to the power 24, which is 16 megabytes of space. And then we declare a huge array, which is again you take 1L, 1 long, and you shift it by 31 bits, and that leads to 2 to the power 21, which is 2 gigabytes of space. And then plus maybe we declare an int here, and then we have a function which doesn't do anything. And inside my main, then we declare we have a number of pointers, and we have again a variable that's local to main, and then we malloc some space within our main. So we do malloc and 1L to the power 28, which is 256 megabyte. We do another malloc for P2, 50 byte, another one which is 4 gigabyte, another one, and then we'll be printing the addresses here. So with this, once you do those allocation, and if you want to then print the addresses of these variables, then you will be seeing, you can actually understand how this memory layout is laid out in the x86-64/Linux system. So you can see, for example, that, so for main and useless, and so if you look at their addresses, these are the addresses for their instructions. You can see that these actually map to this region, starting from 4000, etc. Then we had declared these were my global variables. So this is the text. Then global variables. So we have declared them. You can see that these are mapped to this location, okay, into this region. And then we have this P1 to P4, which were then mapped into the different parts. So you can have like 2 different regions for allocating all. heap. And you can see that these two were mapped to here, whereas these two were mapped these basically regions in the memory layout. And then the local, which was this is part of basically the stack. It's because in the functions, when we declare a local variable, you remember that we were actually allocating space in the stack, and that's why you can see that this address for local, which is declared in our function, its address is showing up in here.